And what we're looking at here on page 39 is just to get a sense of the trends. If I look at period 1, there's only the two elements, hydrogen and helium, in it. And so there's not really a lot to say as far as trends are concerned because there's only the two. Period 2 is this one here where we've got our metals. Over here, technically boron is a metalloid, but we don't talk in terms of metalloids in this course. On your formula sheets, I believe it's a non-metal. Yep. And so we just consider that right-hand side of period 2 to be non-metals. And this is group 3, period 3, sorry, with our metals over here. Aluminium is obviously a metal, and then we say these on the side of the right side of aluminium are non-metals. But what tends to happen what do we know happens if we react sodium, say, with water? What do we form? Sodium hydroxide. And that's why it's an alkali metal. Yeah, an alkaline earth metal in group 2, because calcium would also form calcium hydroxide if it reacted with water. Yeah? So these ones are forming bases. What happens if I react on this side? What do you think would happen? Reaction with, say, chlorine gas with water. Yes, we're going to be forming acids. So, and even if you breathe in sulfurous fumes, then effectively you're going to end up with like a sulfuric acid in your lungs. So if you're breathing chlorine gas was used during World War I. Soldiers were gassed, and it's effectively forming hydrochloric acid in your lungs. So it's burning your lungs. Volcanoes emit a lot of sulfurous gases. You might remember the White Island issue in New Zealand where there was that eruption there. There were two issues, there were two aspects to it. One was the steam, which was superheated steam, basically cooked the people there, but also the sulfurous gases are going to then make it worse by causing a chemical burn effectively as well on that very raw skin or no skin. Not good to breathe these sorts of gases. They are definitely going to cause irritation, at least to the lungs. Right, so if we're looking at it as a period, we're basic over here, and then we get acidic over here. Probably a good time to turn to our trends page on page 40. Because the main one we need to look at is period 3. So if you look at this, we've got the element name, the period 3 in the top row. The second row is the symbol, that's all fairly straightforward. The third row is the atomic number, which again is quite straightforward. And then we've got the electron configuration, which hopefully is also quite straightforward. You can see that for all of them, they have neon in the bracket, and then we're just adding our electrons sequentially to our S subshells and P subshells. Metal or non-metal? Well, again, we can just read this straight off our periodic table if we forget, because we've got that heavy line on there that reminds us where the junction between metals and non-metals are. The chloride formula. Okay, what are these going to look like if they react with chlorine? I think sodium chloride and magnesium chloride and aluminium chloride all look pretty straightforward, don't they? But you would know that the chloride ion has a single negative charge, and so you're going to need 1 for sodium, 2 for magnesium, and 3 for aluminium. Silicon chloride, hopefully again that makes sense. We know that silicon sitting below carbon. Okay, so we know carbon can form 4 bonds. It's not a big leap to decide that silicon forms 4 bonds as well. So it's going to be 4 chlorines. Phosphorus can form 2 kinds of compounds with chlorine, either accepting 3 or 5. Now if we think about where phosphorus is, maybe this might make sense if we're pairing up electrons. If we look at its electron configuration, that it's possible for it to form both of those kinds of compounds with chlorine. Then we get back to sulfur and then chlorine itself, which I think again is pretty reasonably straightforward. Argon is not forming any compound with chlorine. The bonding, again, I think this should be straightforward. Ionic bonding for our metals, and then over to covalent bonding for our non-metals. The formula for the oxide, again, that should be reasonably straightforward, but we'll have a little bit closer look at the formation of oxides. Then we've got this line that says acid-base nature of the oxide. Basic from here, and then this new word amphoteric for the aluminium. Silicon dioxide is neutral. Why is it going to be neutral? What can you tell me about the bonding in silicon dioxide? This is fissile revision.
Covalent bonding?
Yes? No, it's not covalent molecular. Now we already knew it was covalent because it was in that column there, but silicon dioxide is a common constituent of beach sand. Now beach sand is not molecules. Molecules will generally be gases, liquids, soft solids, and so it's not none of those. It's a 3D network structure. It's also known as quartz, and so quartz on most scalar particles has a hardness of 7 and is insoluble. That is why it's neutral. For something to be acidic or basic, we have to be able to dissolve it, because this is a property of releasing ions into solution. Okay, the hydrogen ions or the hydroxide ions are present in solution. That's what makes it an acid or a base. But if you can't dissolve it, then it's neutral. Right? And then, as we've already discussed, these ones over here are acidic, and argon is not reactive. Now, our electronegativity, we can say that over here has lower electronegativity, or we can also describe them as electropositive, as being the opposite of electronegativity. So electronegativity being how well you can accept electrons. This is talking about the ability to donate electrons. Probably best to just stick with the term of high and low electronegativity, because I think that's still clear as far as your communication is absorb. Over here we have powerful reducers, and we know where to find these on our electrochemical series, and we would find them low down on the reducer side of the table. And then if you look from chlorine gas, same we would find it as an oxidizer. And so we've got this trend across the period from decreasing, reduces on this side, oxidizes on this side, getting increasingly stronger as an oxidizer in that direction, and getting increasingly stronger as a reducer in that direction. So if we're talking about our reducers, we're really looking at aluminium, magnesium, and sodium. And we're looking at that side of silicon. The next line is the first ionization energy, and we should be able to account for the dips based on our filling, half filling, or empty filling of our subshells. And then we've got a bit of a dodgy diagram there of the relative atomic radius. Now, you don't need to memorize that because it's on that trends periodic table that's on the formula sheet. You don't really need to memorize much of this at all, but there is something that's important to understand that we haven't really gone into very much detail about, and that is looking at these oxides. Now, when students get tied up in knots or make mistakes with the oxides, is that they start with the metal rather than starting with the oxide. Because what we're talking about here is, well, it's the oxide that's acidic or basic, not the metal itself. So if we think about our reaction with, say, sodium. So if we've got sodium oxide, what are we going to form? Balanced?
No. Is it balanced? Well,
looks like it's balanced
it is, yeah.
to me. So we've got 2 sodiums, 2 oxygens, and 2 hydrogens on both sides. Okay, so here, and it doesn't matter if it's, in this case, it can be a solid. Sodium salts are soluble. Okay, so I'm reacting the oxide with water and my product is basic. Does that make sense? What about magnesium oxide? Figure out how to make this. Can I balance this? Magnesium. Oh. Yeah. So, this is all you need to be able to show why the oxide is basic. Because for it to be either an acid or a base, it has to be in water. Now, in actual fact, this is a solid. Now, I'm using hydroxide will form a solid, but some of it will go into solution, and if there's some of it, a tiny amount in the solution, it will be basic. Question for you. This was on an exam a couple of years ago. Are these strong bases or weak bases? I just told you that this is a solid, so most of it's going to stay as a solid.
Sodium hydroxide certainly is strong base.
Okay, so this one's strong. And the actual question on the exam, I'm pretty sure it was calcium hydroxide. What's the definition of a strong base? What does it need to do?
When it goes into solution, all of it breaks into the with ions.
Fully ionized, is this
Yeah.
right?
It fully ionizes when it breaks apart, yeah.
If it's a solid, doesn't that mean
Well,
it's different and it's weak if it's fully ionized?
not necessarily.
Or what we have to not concentrate on is the part that's still solid. What we have to think about is what's happening in the solution. So these are both strong. Because the part that does break apart, does go into solution, will completely ionize. Well, because these are, think about what else our weak bases are, or our weak acids are, and they're organic. And so they stay as a molecule, whereas these are ions. This is ionic bonding, not covalent bonding. And so, do you remember the one from Visai, who said that this was only partially ionized, so most of it is like that. Most of it's the molecule. Yeah? So these aren't molecules, these are ions. Once they're in solution, they are completely separated, and that's the definition of a strong acid or base. So don't worry about how soluble it is. Whatever ions are in solution, it's completely separated, so it's very crystal. That's my. I wish I had my other one. I like the other one better. And then we've got our oxide of sulfur. And if you look at the table, you've got, I'm sure they're the two oxides that we're given. Yeah? Yeah. I'll stop looking for it. And so this is the outside of the periodic table, and this is what you're often asked to look at. And what do you think I'm going to be able to do with these? This one will make sulfuric acid. So this one here is a strong acid. This is weaker. It's not as strong. But it doesn't matter. All you have to prove is that it's forming an acid. So I would suggest that this is the easier one for you to learn how to write out as an equation for an oxide. Just because it's making something that you're familiar with. Let's see how they all balance pretty well. We're not hard to balance, but they're really hard to balance if you forget to put the oxygen there. Okay, that, I said that's the main issue is that students just try and write things without having the oxygen there. And I guess the other thing to remember is you're not forming an acid or a base without water. So it's got to be a reaction of the oxide with water to form either an acidic or basic solution. And our last one that we have to think about, they have the strange word, amphoteric, which means that depends on the situation, it can act as an acid or a base. Is aluminium. Okay, so aluminium oxide can act as an acid or a base. Now, let's just have a think about what is an acid. This is really part of Criterion 6, but it might help you understand this. What is an acid? Hydrogen on it. Okay, if we think about our subatomic particles, or our particles within the atom, what is a hydrogen atom?
Proton.
It's a proton. And so, in actual fact, our definition of an acid is it is a proton donor. And our definition of a base is it's a proton acceptor. And so you could technically be given an equation, maybe, depending if this question is on an exam or a test, and you could be asked to say, is the aluminium oxide acting as an acid or a base in this example? And what you're looking for is, well, is it accepting or donating a proton? We don't really need to go into too much detail with it, but you do need to know that the aluminium oxide is amphoteric, and that means that it can act as an acid or a base. So if we look at the example in the booklet, we have A plus 6HCl goes to 2AlCl3 plus 3H2O. So here we also have aluminium oxide, sodium hydroxide, and water forming a complex. So I think in the booklet it's all right. Yeah. So it's reacting with the acid here. So when it's reacting with the acid, it's going to be acting as a base, and when it's reacting with the base, it's going to be acting as an acid. But this is a complex reaction here, and we could work out where the proton's going, but that's not really important for this stage, because we'll look more at acids and bases when we get onto Criterion 6, which will help you with this kind of thinking. So has anyone got any questions about acids and bases and amphoteric.
Is the aluminium oxide the only amphoteric?
It's the only one in period 3, and that's all you need to know is for period 3. That's why it's in here. Yeah. So you do need to be able to write out those other reactions with oxides for anything like period 3. And that's really all of the theory. There are a few more pages going on, we're talking about trends down the groups, which is really all revision from this side. And then there are the remaining review questions. So, I'll give you a couple of minutes. It's 9:30. Let's say 15 minutes to be working on the questions, and then I'll start doing the demo.